There's a stretch of American coastline where this ground is quietly loading itself like a drawn bow, and almost nobody standing on it can feel a thing. Right now, beneath the forests and the fishing towns and the sleeping cities of the Pacific Northwest, two enormous slabs of the planet are locked together, straining against each other, storing up more than 3 centuries of pent-up force. When they finally let go, the coast could drop by 2 meters in a matter of seconds. The shaking could last for minutes instead of the usual terrifying handful of seconds, and a wall of ocean could come racing toward the shore with almost no warning at all. Nearly 13 million people live in the path of this thing, and the scientists who study it are no longer asking whether it happens. They are asking when, and lately, some of them have started to suspect the answer is closer than we'd like. If that sentence made the hair on your arm stand up, stay with me and consider subscribing, because what these researchers have uncovered in just the past year genuinely rewrites the story of the most dangerous fault in North America. Let me tell you what we're actually dealing with, because the scale of it is hard to hold in your head. Off the coast, hidden under hundreds of meters of cold Pacific water, runs a fault called the Cascadia Subduction Zone. It stretches for roughly 1,000 kilometers. From the top of California all the way up past Oregon and Washington to Vancouver Island in Canada. It's the seam where a smaller slab of ocean floor called the Juan de Fuca plate is being slowly shoved underneath the much larger continental plate that carries North America. That word, subduction, just means one plate diving beneath another, and it's happening constantly at about 4 centimeters a year, which is roughly the speed your fingernails grow. Slow, silent, relentless. Here's the problem. The two plates don't slide past each other smoothly. They catch, they stick. The edge of the continent gets dragged down and squeezed, storing elastic energy the way a compressed spring does, year after year, decade after decade, century after century. And a subduction zone like this one is capable of producing the single most violent kind of earthquake the planet can make, a megathrust quake, magnitude 9 or higher. I want you to really understand what magnitude 9 means, because the number by itself doesn't do it justice. The scale isn't linear. Each whole step up isn't a little more powerful, it's dramatically more powerful. Going up 1 full magnitude means 10 times more ground shaking and about 31 times more energy released. So a 9 isn't a bad earthquake. It's in a category almost outside normal human experience. These quakes are so rare that only a small handful have ever been recorded anywhere on Earth. Whole generations of people can live and die without ever feeling one. But when a magnitude 9 finally strikes, it doesn't just damage a region, it changes it permanently. The energy unleashed is comparable to millions of the most powerful bombs ever used, all detonating at once, deep beneath your feet. It is, quite simply, one of the largest releases of energy the surface of this planet is capable of, and Cascadia has done it before. We know it has. That's not speculation, and later I'll show you exactly how we pinned down the date of the last one to a single winter night more than 300 years ago, using clues scattered across 2 continents. But first, there's a discovery from just last year that made this already frightening story considerably worse. Because it turns out the Cascadia fault may not be a lone gunman. It may have an accomplice. Before I get to that, drop a comment and tell me, honestly, did you already know there was a fault like this off the American West Coast? Or is this the first you're hearing of it? I'm genuinely curious how many people are learning about this today. Because for something that threatens 13 million lives, it flies under the radar in a way that still amazes me. Now, that accomplice. For decades, seismologists wondered whether big faults could talk to each other, whether one monster rupturing might nudge another monster into rupturing too. It made intuitive sense, but proving it with real-world evidence was almost impossible. The events are too rare and too old. Then, in a study published in the journal Geosphere in late 2025, a team led by marine geologist Chris Goldfinger of Oregon State University laid out the strongest case yet, and the way they stumbled onto it is almost too good to be true. Back in 1999, Goldfinger and his colleagues were on a research vessel studying Cascadia by drilling long cylinders of mud out of the seafloor, called sediment cores. These cores are like history books written in layers. But one night, a graduate student typed the wrong coordinate into the navigation system, and the ship drifted far off course, ending up about 90 kilometers south of Cape Mendocino, California, well outside the Cascadia Zone, and squarely in the territory of a different, equally infamous fault, the San Andreas. Goldfinger woke up annoyed. Then he shrugged and thought, well, we're here anyway, might as well take a core. That accidental core cracked the whole thing open. When they examined the mud, they found layers called turbidites. These are deposits left behind when underwater landslides come roaring down submarine canyons, and those landslides are very often triggered by earthquakes. A big quake shakes loose a slurry of sediment. It flows downhill along the seafloor, and it settles into a distinctive layer, coarse grains at the bottom, fine grains on top. Each layer is essentially a fossil fingerprint of an ancient earthquake, And in this accidental California core, going back some 3,000 years, the team noticed something bizarre. Many of the layers came in pairs. A finer deposit and then a second coarser, sandier deposit right on top of it. Doublets, they called them. And at first, they were completely baffled. Then they dated everything using radiocarbon, and the second shock arrived. When they lined up the earthquake records north and south of Cape Mendocino, more than half of the events matched in timing, within the margin of error of the dating method. That was far too many overlaps to be coincidence. Something was making these two separate fault systems rupture at nearly the same moments in history. The light bulb moment was this. When Cascadia unleashed a great quake, it sent a weak turbidity current sliding down near the San Andreas. Then, sometime later, the San Andreas itself ruptured, sending a second, much heavier, sandier flow down on top of the first. That's what created the upside-down pairs in the mud. And in some of the deposits, the evidence suggested the second earthquake followed the first within minutes to hours, not centuries apart, not even days, practically back-to-back. Sit with the implication of that. It means that when Cascadia's so-called big one finally arrives, it might not come alone. It could set off a major rupture of the northern San Andreas, the same fault system that leveled San Francisco in 1906. Goldfinger himself put it bluntly, calling the possibility of a San Andreas quake following Cascadia movie territory. A magnitude 9 in the Pacific Northwest, and then, hours later, a huge quake tearing through Northern California. Seattle, Portland, San Francisco, and Vancouver all reeling within the same terrible window. A double catastrophe stretched across the entire west coast of the United States, potentially killing thousands and inflicting damage measured in the hundreds of billions of dollars. Goldfinger, who grew up in the Bay Area, said if Cascadia went off while he was home in Palo Alto, he'd get in his car and drive east as fast as he could because he'd expect the San Andreas to follow. So the obvious question becomes, when? When does this happen? And to even begin answering that, scientists first had to figure out exactly when it last happened. That detective story is one of the most remarkable pieces of science I know, and it starts not with instruments, but with stories. Long before there were seismographs, the people who lived along this coast carried the memory of a great shaking in their oral traditions, passed carefully from one generation to the next. On Vancouver Island, the New Cha Nulth told of tiny mountain beings who invited people to dance around a drum. When someone kicked the drum by mistake, a dancer was cursed with what was described as earthquake foot, and every step they took made the ground convulse and the sea rush ashore, so suddenly that people couldn't even reach their canoes before their world vanished beneath the water. And they weren't the only ones. A research team at the University of Washington, led by Ruth Ludwin and bringing together anthropologists, geologists, and indigenous scholars, studied roughly 40 stories from native communities running all the way down the coast from British Columbia to California, groups like the Yurok, the Tolowa, the Squamish, the Tillamook, and the Quileute. And what they found was astonishing. Across hundreds of kilometers from different peoples and different languages, the same essential event kept surfacing. The ground heaving violently, the ocean drawing back and then charging in, landslides swallowing whole villages. These weren't vague myths. They were eyewitness accounts of a real disaster, preserved across centuries. The problem was that the precise date had faded with time. To lock it down, scientists needed another kind of witness, and they found one standing silently along the Oregon coast. It's called the Niskowen Ghost Forest, and it is exactly as haunting as it sounds. A cluster of ancient western red cedars, long dead, their weathered trunks jutting up out of a salty tidal marsh like the bones of a drowned world. For years, people assumed those trees had simply been killed off gradually as sea levels crept upward and poisoned their roots with salt water. But in 1987, a geologist named Brian Atwater from the U.S. Geological Survey published a landmark paper in the journal Science that told a very different story. Atwater studied the buried soils beneath the marsh, and he realized the trees hadn't died slowly at all. The land had dropped suddenly, subsiding by as much as 2 meters in one violent instant, letting the ocean pour in and drown the forest almost overnight. And pressed into that same buried soil was a thin layer of sand deposited from above. That sand was the signature of a tsunami, a huge wave that had swept inland and left its mark. So now there was hard physical proof of a massive earthquake and a great wave. But the same maddening question remained. Exactly when? To crack the timing, Atwater joined forces with David Yamaguchi, a scientist who studies tree rings, a field called dendrochronology. And tree rings, it turns out, are one of nature's most precise clocks. Every year a tree lays down a new ring. Fat rings in warm, wet years. Thin rings and harsh ones. Reading them is like flipping through a diary written in wood, 1 page per year. Yamaguchi compared the dead cedars in the ghost forest with living trees nearby, hunting for the exact moment when the doomed trees stopped growing. And he found it. The outermost ring on the dead trees had formed in the year 1699. Deeper analysis of the roots narrowed it further to the winter, spanning 1699 into 1700. Close, but still not the precise moment. And here's where the story does something almost cinematic. The final piece of the puzzle wasn't hiding anywhere in North America. It was waiting more than 8,000 kilometers away, on the far side of the Pacific Ocean, in the meticulous written records of Japan. Japan sits at the meeting point of several tectonic plates, which makes it one of the most earthquake-prone nations on Earth, recording well over 1,000 quakes every year. The people there have documented tsunamis in extraordinary detail for more than 1,000 years, noting wave heights, flooding, damage, and precise times. In the 1990s, a geologist named Kenji Sadake with the Geological Survey of Japan was combing through these old records when he found an entry that made no sense. The documents described a night in January 1700 when the sea suddenly rose and struck the coast, flooding homes, sweeping structures away, sparking fires, wrecking ships, and killing around 1,000 people, whose bodies washed ashore as survivors scrambled for high ground. But there was one detail that stopped Satake cold. Not a single record mentioned an earthquake beforehand. In Japan, where people knew earthquakes intimately, no one had felt the shaking that should have come first. It was a wave from nowhere. Historians ended up calling it the orphan tsunami, a deadly flood with no known parent. Satake and his colleagues solved the mystery by working backward. Using the detailed Japanese records and computer modeling, they reconstructed the size and location of the earthquake that must have generated those waves. And the answer pointed straight across the ocean, to Cascadia. A magnitude 9 rupture off the coast of the Pacific Northwest had thrust up a vast section of seafloor, displacing an enormous volume of water and sending waves racing across the entire Pacific. By the time they reached Japan, roughly 10 hours later, they were still tall enough to kill. The wave was an orphan in Japan only because its parent had struck an ocean away. And when the scientists combined everything, the Japanese timing, the tree rings, the sediment layers, the drowned forest, and the indigenous oral histories, they arrived at something remarkable. They pinpointed the last great Cascadia earthquake to the night of January 26, 1700, at roughly 9 in the evening local time. A single silent rupture beneath the ocean that reshaped coastlines on 2 continents in one night. Which brings us right back to the question that matters most. That was over 325 years ago. So how much time do we have left now? Over those 3+ centuries, the strain has been quietly accumulating along Cascadia, the Juan de Fuca plate grinding beneath the continent, the spring winding tighter and tighter. And the truly unsettling part is that we're not guessing about this anymore. We are, in a very real sense, watching it happen live. In 2021, a team boarded the research vessel Marcus G. Langseth and set out to essentially give the seafloor a medical scan. They used powerful air guns to fire pulses of sound down through the water and into the crust, then listened for the echoes bouncing back, using more than 1,000 underwater microphones strung along a cable stretching some 15 kilometers behind the ship. It was, in effect, a giant ultrasound of the Earth's interior beneath the ocean floor. The data was so vast that key findings weren't published until 2025 in the journal Science Advances, in a study led by geologist Brandon Shuck, now at Louisiana State University. And the images it produced are the clearest we've ever had of Cascadia's hidden structure. What they revealed was not a plate sliding down neatly and smoothly. Instead, the Juan de Fuca plate is fracturing as it descends, breaking into segments, with huge slabs peeling off and sinking deeper into the mantle. In one place, a tear had dropped a massive section of the plate downward by more than 3 miles. Shuck described it in a way that stuck with me. He said, "This is the first time we've had a clear picture of a subduction zone caught in the act of dying. The fault hasn't fully torn through the plate yet, but it's close." And this matters enormously because if the plate is cracking and splitting as it goes down, that could change how stress builds and releases along the fault above it, which means the next rupture might not behave the way older models assumed. That's not the only fresh clue. In separate research published in the journal Science, a University of Washington team led by Malene Kidawela used an underwater observatory, hundreds of miles of cabled instruments planted on the seafloor, to listen to the faint seismic noise coming out of Cascadia. Unlike the loud, chatty subduction zones off Chile and Japan, Cascadia is eerily quiet, which has always made it hard to read. But by measuring that subtle noise, the team detected strain quietly building in the northern part of the zone. And their conclusion was chilling. The northern section, they found, could rupture differently from the center, with the potential for even larger events, offshore quakes powerful enough to launch a tsunami even if people on land barely feel the initial shaking. So let's take stock of what all this new science tells us together. We know a Cascadia megaquake has happened before. We know almost exactly when. We know the pressure has been building for over 3 centuries. We can see the fault straining and fracturing in real time. The only thing we can't do, despite all of it, is name the day. But we can talk about the odds. And the odds are why researchers keep sounding the alarm. Chris Goldfinger's team reconstructed Cascadia's deep past by reading those seafloor sediment layers, dating the coarse, sandy deposits that mark ancient megaquakes with radiocarbon, and building a timeline reaching back nearly 10,000 years. Over that span, they counted somewhere between 41 and 43 major subduction earthquakes of magnitude 8.2 or greater. The range is fuzzy because we're talking about events that struck long before anyone was writing anything down. For a long time, scientists assumed these disasters arrived on a fairly regular schedule, roughly one every 500 years. But the emerging record turned out to be messier and far less predictable than that tidy number suggested. Here's where the current official estimates land. Scientists put the chance of a magnitude 7.1 or larger quake in the zone at about 37% within the next 50 years. And for the full-length rupture, the true nightmare scenario, the roughly magnitude 9 event, the USGS puts the odds at around 10 to 15% over the coming decades. That might sound reassuringly low until you frame it the way the paleoseismologists do. We have already gone longer without a major Cascadia earthquake than we did in about 75% of the intervals over the past 10,000 years. Push that window out 50 more years, and that figure climbs toward 85%. In the plain, uncomfortable language of geology, we are creeping past overdue. And overdue is not a word anyone wants to hear, attached to the most dangerous fault on the continent. So picture the moment it finally lets go. What does the big one actually look like? The destruction begins within seconds. Shock waves blast outward from the rupture at nearly 5 kilometers per second. The ground doesn't shake for a few seconds the way it does in a typical quake. It heaves for several minutes, an eternity when buildings are failing around you, and aftershocks will keep rolling in for months afterward. Computer models paint something close to apocalyptic. More than 1 million buildings damaged beyond repair or outright collapsed. Highways buckling and splitting, bridges failing, landslides ripping through hillside communities. By the time the shaking stops, power, cell service, and running water may all be gone across huge areas, leaving millions of people stranded. And if it strikes at night, all of that unfolds in total darkness. Then there's a strange and horrifying phenomenon called liquefaction. When violent shaking hits certain kinds of wet, loose soil, the water trapped between the grains builds up pressure and forces the particles apart, and the ground stops behaving like solid earth and starts behaving like a liquid. Buildings can sink several meters, cars can be swallowed whole, and this isn't hypothetical for the region. Roughly 15% of Seattle sits on ground vulnerable to liquefaction, and Portland's industrial district is known to be at risk, which is especially frightening because that area is threaded with fuel and gas pipelines. If the ground turns to liquid and those pipes rupture, a single spark could set off catastrophic fires and explosions. And even after all of that, the worst may still be coming from the sea. If the rupture is offshore, coastal towns could have as little as 10 minutes before the tsunami arrives. Models suggest walls of water reaching 24 to 30 meters high, slamming into parts of the Oregon coast, moving at speeds around 800 kilometers per hour, comparable to the devastating tsunami that struck Sumatra in 2004 and killed around 230,000 people. Some places could be flooded up to 16 kilometers inland by surging, debris-choked seawater as tall as a 3-story building. And these aren't ordinary waves. Scientists classify them as shallow water waves, with wavelengths stretching hundreds of kilometers, which means the gap between one wave and the next can be as long as 2 hours. The danger doesn't end when the first wave retreats. The flooding can last for hours, and the outflow can drag wreckage and people back out to sea. The waves would even cause damage across the ocean, reaching as far as Hawaii and Japan, just as they did in 1700. The human toll in these projections is staggering. According to FEMA estimates, a full magnitude 9 rupture could kill on the order of 13,000 to 14,000 people across Oregon and Washington, with the tsunami responsible for the majority of deaths and injuries. Tens of thousands more would be hurt. Over 1 million people could be displaced. The immediate cost could exceed $150 billion, and some longer-term recovery estimates run far higher, making it potentially one of the costliest natural disasters in the nation's history. I know that is an enormous amount of grim to absorb. So let's turn toward the part that actually offers some hope, because people are not sitting still. In April 2025, a coalition of leading earthquake scientists across the Pacific Northwest, working with the University of Washington, and backed by a major National Science Foundation grant, pushed forward on a mission built specifically around surviving a magnitude 9. A big focus is escape. Roughly 70,000 people live inside what's called the inundation zone, the low coastal ground the tsunami would flood, and in the worst case, some of them might have less than a minute before the first wave hits, when the nearest high ground could be 8 kilometers away, and the water is moving faster than any person can run. Simply telling people to flee isn't enough. So some communities are getting creative. Back in 2022, the Shoalwater Bay Indian tribe in Tokeland, Washington, decided not to gamble on speed or luck and built the first tsunami vertical evacuation tower in the United States. It stands about 15 meters tall and can shelter up to 400 people. It's anchored on deep concrete pilings driven far into the earth, engineered to ride out the shaking of a once-in-2,500-year earthquake, resist liquefaction, and withstand several meters of sideways ground movement. It sits right in the heart of the community as a last refuge, somewhere to climb when there's nowhere left to run. But only a couple of others like it exist so far, with another planned for Westport, Washington, and experts warn it's nowhere near enough. Modeling suggests something like 50 such refugees would be needed to properly protect the coastal populations of Oregon and Washington. These towers borrow their design from Japan, a country that has essentially built its entire civilization around living with this threat. Japan has endured more than 140 destructive tsunamis since the year 684, which have killed well over 100,000 people. The very word tsunami comes from Japanese, meaning harbor wave. In response, Japan has constructed some of the most advanced defenses on Earth, from massive underground flood control systems to hundreds of kilometers of seawalls, some rising 15 meters high, along with rapid early warning systems that can alert the public within minutes of a quake. But their most powerful defense isn't concrete at all. It's culture. Generations of Japanese have grown up understanding the risk in their bones and knowing, instinctively, exactly what to do and where to go the instant the ground moves. The Pacific Northwest, by contrast, is playing catch-up. The threat is every bit as real, but preparedness lags well behind. A lot of older infrastructure remains vulnerable, warning systems are still being expanded, and public awareness is patchy, which raises the question for anyone living there, or anyone who loves someone who does. How do you get ready? Some Oregon residents are already building 2-week emergency kits, a sober acknowledgement that after a great Cascadia quake, entire communities could be cut off from the outside world for as long as 2 weeks, with roads shattered and bridges down. Officials are urging people to sign up for emergency alerts, to pay attention to official warnings, and above all, to learn their evacuation routes now, cold, before the ground ever starts to move. The idea is to rehearse your escape while your mind is calm, because when the shaking begins, there won't be time to think, only to run or to climb. Here's the second thing I'd love your thoughts on in the comments. If you lived on that coastline, knowing everything you now know, would you stay? Or would you move somewhere the ground doesn't do this? There's no wrong answer, and I think the reasons people give will say a lot about how we each weigh risk against the places we call home. For the millions living along the Pacific Northwest, all of this is a reminder that the earth beneath us is never truly still. Under that gorgeous, misty coastline, immense forces are grinding away every single second of every single day. The encouraging part is that we've never understood this fault better than we do right now. We can watch it strain and shift and fracture in real time. We can read its long, violent history in mud and tree rings and centuries-old Japanese ledgers. We've learned to recognize the warning signs written into the planet itself. And yet, for all our satellites and sensors and supercomputers, the one thing we still cannot do is tell you the day it will happen. But this much is certain. One day, and quite possibly within the lifetime of someone watching this, the strain will win. The seafloor will lurch upward, the coast will convulse, and the Pacific will come surging inland the way it did on that January night in 1700. The last chapter of America's great megaquake hasn't been written yet. But far below the surface, in the dark and the silence, the pressure is already building toward it, one fingernail's width at a time. If this opened your eyes to something you'd never really thought about, do me a favor and hit that like button, because it genuinely helps more people find this and get informed. Subscribe to W for Weather, so you don't miss the next deep dive into the forces shaping our planet. And I meant what I said earlier. Get down in those comments and tell me whether you think this quake is imminent, and whether you'd ever live on that coast knowing what's coming. I read them all, and I'll see you in the next one.